The name of this video is Magnetic Dipole Moment Part 2. The idea of this video is to find a more manageable expression for A1 at the observation point R. So let me remind you what is A1 at the observation point R as we found it in the previous video. So this is given by minus mu naught divided by 4 pi, volume integral in the region where J is defined, omega, capital omega, of 1/2 of JR prime, J vector, at the source current point R prime, the whole quantity times R prime dotted with the gradient of 1/R minus, I swap the role of R prime and J, so R prime I take it outside and I dot it and I multiply it without dotting it. The dot I keep it inside, so I swap just the role of J and R prime as we were seeing in the previous video. And so here I take inside J vector at R prime, here dotted the gradient of the variable I'm not integrating, which is 1/R. The whole quantity times 1/2, the whole quantity in dV, which is dr prime cube. Great. So now we want to find a more manageable expression for this. In order to do so, we need to remind ourselves that the product of three vectors for any term of vectors A cross B cross C can be rewritten as A dot, which gives a scalar, C, B, which gives me the direction and a vector, minus A dot B, again, the scalar part, and the direction, which is C. A dot CB minus A dot BC. The mapping we need to do between this expression and this vector relation is as follows. We call A, if you observe closely this expression up here, gradient of 1/R. We call B, J vector and R prime vector. And we call C vector simply R prime vector. All right, so with this substitution, what we eventually get, so now if we rewrite this expression up here, using this, if you do this mapping, you will find out that A1 of R, I'm skipping a few steps, you can do them if you want, you can show them to me in Piazza, they're relatively simple. So we keep our sign minus mu naught over 4 pi, so now let's note that eventually there is a gradient of 1/R, which has to be crossed with some, because in the end what we are doing, we have this expression here is nothing but this kind of expression on the right hand side, and we want to recast into this, so this is nothing but that, okay? So eventually this integrand becomes A vector B vector C, where A, B, and C are defined here, okay? So clearly the gradient of 1/R crosses the rest of the integrand, but the gradient of 1/R is not a function we are integrating on, because it's only a function of R, so I can take it outside the sign of integral, and so I obtain minus mu naught over 4 pi, gradient of 1/R, which is a vector, and this vector crosses the volume integral in the region omega space of B vector C, which is nothing but J at R prime crossed with R prime. The whole thing in the R prime quantity cube. Now, here you should see somehow a definition which is a weighted average similar to that for the dipole moment. So we have J weighted with R prime with a cross product because they are vectors, okay? Now, however, in the definition we use in the electrostatic case, in the electric case, we had the weighting function was before, so it was R prime times rho of R prime. Now, in that case, it doesn't matter because it's just a regular product. Here is a cross product, and in order to keep it exactly in the same order, it's worth swapping these two functions here. And when you do this swap, obviously you pick up a minus sign. And why is that? Because the cross product is non-commutative. So this minus sign, which I pick by swapping this, cancels this minus sign. Therefore, leaving us with A1 at R, which is going to be plus mu naught divided by 4 pi. Now we have the gradient of 1 over R. We keep it right there. Which is crossed with the integral in capital omega. And of course, the only thing I've done here, I forgot to put the factor of 1/2. So this quantity here is the one which is transformed in this fashion without this factor of 1/2. So we need to remember this factor of 1/2, which is important. So we have 1/2. This is a little bit of a difference compared to the dipole case, but that's the way it is. So it's 1/2, and then I'm weighting with R prime what I cross it, the J R prime. So weighted average in a vector sense, okay? The R prime cube, right there. Great. So now with this, let us define this quantity here. Again, caveat, there is a factor of 1/2, not to be forgotten. This quantity, we define it as m vector, and this is nothing but the dipole moment. Equivalent to p vector in the case of the electric field. In this case is m vector, okay? All right, so now what we have here is worth rewriting this as the, so let me continue up here. So this quantity here, A1 of R, let me rewrite it one more time as mu naught over 4 pi. Now let's swap this m with the gradient, so I get a minus mu naught over 4 pi m crossed with the gradient of 1 over R. So I just swap it. So again, I pick up a minus sign. This is my m. Now we know from several previous videos that the gradient of 1 over R actually is nothing but minus R over R cube, R vector over R cube scalar. In this fashion, okay, with the minus sign. So we should not forget this minus sign, which we pick up there. And so if we substitute it in here, well, then what we get? Finally, we get A1 of R equal, this minus sign cancels with this minus sign, that's why I swap them. And so I get mu naught plus mu naught divided by 4 pi m cross R from the gradient divided by R cube, absolute value. This is the final expression, the more manageable expression we wanted to find from the beginning. So this series of videos eventually leads to this final expression. Now this is interesting because if you remember, in the case of the electric field, we found that if you want, you can call it V1 of at R is given by, instead of mu naught over 4 pi, 1 over 4 pi epsilon naught. Instead of m, we have p, dotted instead of cross, R divided by R cube, where in this case, p, instead of being defined as in this fashion here, is defined as the volume integral is the weighted average of the charge density. To be noted, the difference in this factor of half, which here is not present. Okay, so this is quite interesting. So we found an expression which is similar. The only difference is that m and p are swapped, of course, the peak factors and the cross product instead of the dot product. Now, I want you to think in Piazza about the following issue. So the question I have for you in Piazza is, does it matter the choice? So will m depend on the choice of origins? Or not? Okay? We have proven this in the case of the electric field. We have seen when the dipole moment P depends on the choice of the origin of all vectors and when it doesn't. And here I want to ask you whether it's the same case or it's not the same case. Okay, so to summarize this video, so in this video, it's the last video on the magnetic dipole moment in general. And so I rewrote down the expression for A1 after splitting up this into two integrals. And now we're only left with the one with the minus sign. We use this simple vector identity here, which allows us to recast this integral into this integral down here to remember the factor of 1/2. Then some readjustments of these vector products. And eventually we end up with this expression, which finally gives us the famous result. A1 of r, the dipole moment, is mu0 over 4 pi m vector r over r cube, which is very similar to the p dot r over r cube for V in the electric case. And I'm asking you what happens if I choose a different origin when I intend to compute m according to this definition given here. That's it.